So let us discuss about isomorphic graphs, right? What do you mean by isomorphism in general? So we say mathematically we say that the things are isomorphic if they are almost same. It's not that they look alike. It is that they are going to have the same property. Whatever uh, A is having, all those properties will be satisfied by B also. Okay, a kind of similar behavior like that we take isomorphism means. Okay, so we say that two graphs are isomorphic if they have the same behavior. We can't take that as a general definition, but okay, first we need to define what do you mean by isomorphism, and later we can discuss this. Okay, see, for example, if I have a set 1, 2, 3 and A, B, C. Okay, there are two sets here. Now, here in some sense we can say that these two sets are same. Here I have a set of 3 people and here also a set of 3 people. Just what I'm having is names, that's it. Here these 3 people are named 1, 2, 3 and here the people are named 1, 2, 3. Okay, in some sense both sets are same, right? I mean, this is having 3 people, that is also having 3 people. Alright, so now whenever we have this situation, what you can do, you can actually define a function between them, so that becomes 1, 1 and onto. We can define a 1, 1 function and onto function, and suppose that if these sets are having special properties and we wish that special property, the extra special property, to be satisfied by these elements. Okay, let's assume that here we have some operation, a star. Okay, so here let's assume that if 1 star 2 results something, let's assume that it results some guy. Okay, then under this mapping we defined a function, no, a 1, 1 and onto function here. So we wish that the image of 1 star 2, okay, let me assume that 1 star 2 is 3. Alright, and we do wish that the image of this 1 star 2 is same as image of 3. That is f of 1 star f of 2. Okay, so like in linear transformations you have seen, you say a mapping is a linear transformation if it satisfies this property, no, T of v1 plus v2 equal to T of v1 plus T of v2. Alright, and T of alpha into v equal to alpha into T of v. So you can actually combine these two and you can simply take alpha here and alpha here. Right? So here when I take this function t, whatever the operation we defined here, I'm allowed to operate on this operation, this function. This f of 1 star 2, and this must be same as f of 3 and that must be same as f of 1 star f of 2. This is what we wish. Okay, that may be a multiplication or maybe addition or some binary operation I'm taking between them. Okay, so when it comes to graphs, there the elements you can take vertices. Okay, now between vertices what do we have? For example, if I take a graph, I'm taking a simple graph. So this is a graph, right? Having the vertices A, B, C, D. Okay. Now between A and B, what I have here is an edge. It's like A and B are connected. Okay. So if A and B are connected by an edge, if A and B are connected by an edge, let's say if you define a function f from this set to another set of vertices, let's say you have the vertex set is 1, 2, 3, 4. Okay. So here I'm defining a one-to-one mapping here. So maybe A mapped to 1, B mapped to 2, D mapped to 3, C mapped to 4. Like that I'm mapping. Okay. So if there is an edge between A and B, okay, we must find an edge between f of A and f of B. Okay, it means that if A and B are adjacent in the graph, then f of A and f of B must be adjacent in the other graph. So between two simple graphs, let's say you have a graph, let me take it as V1 comma E1, and another graph that is V2 comma E2. So now when can we define one and onto function? One and onto function is possible from a vertex at V1 to another vertex at V2 if and only if both have the same cardinality. Okay, we would like to define a function so that this function is 1, and the second thing is we want that function to be onto. And moreover, this is the property related to the graphs now. Okay, so that is if A and B are adjacent in G1, if and only if the images f of A and f of B is are adjacent in G2. So then we say that these two graphs G1 and G2 both are isomorphic. So when an isomorphism is possible between two graphs, what is the relation between the vertices set? So one thing we can observe, if we want to define a 1, function between them, definitely, and 1 and onto function, definitely the number of vertices in the first graph is same as number of vertices in the second graph. Okay. Not only that, the third condition tells that the number of edges must be same here and there. Okay, that we can tell from the third condition. You can't say that just using the two conditions. Okay, if you have just one and onto function, we can't say that that is an isomorphism. Okay, I'll give you an example. For example, you take these 2 points. Okay, this is G1, and I'm taking another 2 points here. but they are connected by an edge. This is G2. Number of number of vertices here are same as the number of vertices here, but these are not isomorphic. Okay, here, okay, you can satisfy the first condition. You can define a one and onto function from here to here. Simply what you can do, you can map this vertex to this vertex and this vertex to this vertex. Fine. But the third condition is not getting satisfied. So here, these two vertices are adjacent, but in the graph one, those two vertices are not adjacent. Okay. So first two conditions are not alone enough to say that graphs are isomorphism. Okay, if you have a bisection, I can't say that the graphs are isomorphic. Along with bisection, you need this condition also. All right. Now, okay, let's look at an example. So let me take C4. You know what C4 is? This is C4, right? And let me name the vertices as A, B, C, D. Okay. And here I am taking another graph, which is let me name it as just G. Okay. So this is 1, 2, 3, 4. All right. So two graphs I'm taking. One is C4, another one is G. Now the question is C4 isomorphic to G? We know the definition of isomorphism. You must be able to define a bisective function from C4 to vertices of C4 to vertices of G, so that if A and B are adjacent here, their images are also adjacent in the other thing. Right? No. Are they not isomorphic? All right, let's see. So now let me try to define a function here. So here, let me define a function from vertices of C4 to vertices of G, where you know V1 is nothing but A, B, C and D, and whereas V2 is 1, 2, 3, 4. Now this is how I'm defining a function. Now f of A, I will map it to 1, and f of B, now I will map it to 2, and f of C, I will map it to 4, not 3. Okay, and f of D, I will map it to 3. Okay, now this is clearly a bisective function. Now, is it satisfying the third condition? So let's see. Anyway, there are only 4 edges. Yeah. So here are also 4 edges. So let me see. Here, there is an edge between A and B. So let me write the edges in C4. What are edges in C4? That is AB, right? And similarly, you can see BC and CD and DA. These are the edges in C4, right? Now let me see the images. So what can you say about f of A and f of B? What is f of A here? F of A is 1 and f of B is 2. Okay, and we have this edge 1 comma 2, and this is same as f of a comma f of b. I mean this 1 2 edge is here. Okay, now for this particular edge we got an edge here. Next, let me take the edge BC. So now if it is BC, you know what is the image of f of c, right? What is the image of f of c? F of c, we mapped it to 4. Okay, now do we have f of b comma f of c edge? It means 2 comma 4. Are 2 and 4 connected here? Yes, 2 and 4 connected. Okay, so now for this particular edge, the corresponding edge is here. So therefore, so the edge 2 4 is representing f of b and f of c. And similarly, let us look at the CD. So for that, let me see what is the image of D, but that is 3. Okay. Now, do we have this edge, which is 3 4? Let me see. Yeah, here you can see 3 4. All right. So 3 4 is here, and that is related to C and D here. So which is f of D and f of C. Okay, it doesn't matter in which order you wrote, because they are sets, no? If it is an ordered pair, the order is important. So the next one, definitely you look for the edge f of D and f of A. What is f of D? F of D is 3 and f of A is 1. So do we have this edge 3 comma 1? Let me see. Yeah, 3 and 1 are connected here. So this is related to the A and D, and the corresponding edge is here. Alright, so the only thing what you have to do is, it's like this. You take 2 sticks, okay. You take 2 sticks like this. One is here and below is 1, and you tie a thread to it here and here. Okay. If you simply flip it, you will get. If you rotate the below one, you will get this one. Understand? So it is possible to obtain other graph using this graph. That's what it means. So both graphs are isomorphic, because we are able to define a bisective function between the vertices of 2 graphs so that they satisfy this property. Like if A and B are adjacent, then their images are also adjacent here. Therefore, these 2 graphs are isomorphic. Therefore, the question answer to this question is yes, they are isomorphic. Okay, so just by seeing, we can't easily say. I mean, because sometimes, I mean, you may think that here the intersection happened, there the intersection not happened. But we can actually redraw this graph so that no intersection occurs like this. You understand? The only thing you just change the vertices position so that you will get the other one. So isomorphism, it means the same thing. I mean, you can reassign the vertices name so that you will get one graph using the another graph. That's what. Okay. So since here you have 4 vertices and only 4 edges, so you easily identify an isomorphism between them. But what if you have a big graph, for example, Um, let's say you have a graph, one graph like this with 5 vertices, okay, and another graph is, how many vertices are there? One, two, three, four, five. Okay, it means I don't need this guy actually. Do you connect this to here? Something like this. Yeah. So how about this graph? These two graphs. 4 is here. Okay. I mean, every time finding bisector function is not so easy. Okay. So now in that case, what we have to do? So initially I told isomorphism, it means we say two guys are isomorphism, they are means that they have the same properties or the same behavior. Okay. Okay, now we will check the properties. Like if they do, I mean, if they differ by some property, then we say that they are not isomorphic. Okay, and also we need to take care, I mean, take the properties that are invariant under isomorphism. Okay, you can't say that, sir, here in the last problem, here the lines are intersecting, here the lines are not intersecting, therefore both are not same. Okay, it is not about intersection. Since it is a graph, okay, we are interested in adjacent vertices. That's it. Now, what are the properties that are invariant under isomorphism? So that we need to know first. So one thing, number of vertices, that is trivial, you know. So if G1 is isomorphic to G2, so here the number of vertices will be same as the number of vertices of G2. And similarly, number of edges in G1 must be same as number of edges in G2. If they differ by these two, then we say that okay, they are not isomorphic. G1, G2 are not isomorphic. And next thing is you can look at degree of vertices here. Okay, now how do we compare degrees of vertices? Because you will have 10 vertices here, each vertex will have some degree, and similarly on the other side you'll have 10 vertices, each vertex will have some degree. Now how do you know that whether the all degrees which are there are given here or not? So for that we will do one thing. You better arrange the degrees in a decreasing order or non-increasing order. For example, let's say you have a graph, it has 5 vertices and the degrees are like 3, 2, 1, okay, and so on. So we are going to arrange the degrees in a non-decreasing manner. We will keep the highest degree. Next, the either the degree which is equal to the previous one or less than that. So we will keep it in a non-increasing order. So now you see, for example, we got the sequence 3, 2, 2, 1, 0. Okay, so this is the sequence we occurred in G1. It means degree of one vertex is 3, another vertex is 2, another vertex is 2, and next one is 1, and the next one is 0. Similarly, here you arrange the terms. Suppose if you get everything is 2, 2 here, let's say 2, 2, 2, 1, 1. Then they are not isomorphic. Okay, the degree sequence must be equal. and we have a name for the degree sequence. For example, if we have a sequence, first of all, I wrote some sequence here, right? That is 3, 2, 2, 1, 0. Can we have a graph with this sequence where it is degree of one vertex and 2 is a degree of another vertex, like that? Can we have a graph with this sequence? First of all, we need to take sum of all these degrees. What is the sum? Sum is 8. Okay, it is an even number. Suppose if it is an odd number, okay, then we are sure that there is no graph with these degrees, with 5 vertices. Because you know handshaking theorem, right? So using that we can easily tell sum of the degrees of all vertices must be 2 into m, 2 into number of edges. Alright, now what is the graph? I would like to draw the graph here. So there is one vertex of degree 3. There is one vertex with degree 3. Okay. Next, let me take this vertex with degree 2. So let me simply connect to it. So that this will have degree 2 and this will have degree 2. Alright. Now I cannot connect this one to this one, because if I connect, what happens? Then it is going to have degree 3. Alright. So now there is a vertex with degree 1, okay, which is given here, 3 degree here, and there is a vertex with 0 degree. That's it. Alright. So for this sequence we have a graph, right? So we call this sequence as graphic. So you take sequence of degrees. For example, you write some random sequence with non-negative numbers. Okay, that too an non-decreasing sequence only. Sorry, non-increasing sequence. If there is a graph which match with that sequence, then that sequence is going to be graphic. Otherwise, it's not graphic. Okay, so the sequence what we wrote is a graphic. Alright, so you can compare degree sequence of two graphs, graphics of two graphs, that you can compare, and using that you can, if they differ, then you say that both are not isomorphic. Okay, let us look at an example. Let us look at an example here. Let's say so this is G1. I'm taking this one as G1. So there are how many edges are here? 1, 2, 3, 4, 5. So here 1, 2, 3, 4, 5. Yeah. So are they? Let me assume this is G2. Are they isomorphic? G1 and G2? No, they are not isomorphic. Okay. So why they are not isomorphic? So let me write the degrees of each vertex. On top of it, let me write a degree. For example, this vertex, the degree is 2, 2, 2, 2, 2. Every vertex here is of degree 2. Okay, I'm not writing names. Okay, this is actually degree. I'm writing degree. But when it comes to G2, you see the degrees here. So its degree is 2 and its degree is 3. That's it. It is enough. No need of looking at the entire sequence. In G1, every vertex is of degree 2. But in G2, we have a vertex of degree 3. Now this is enough to say that both graphs are not isomorphic. So G1 is not isomorphic to G2. We can write the reason. G1, G3, G2 has a vertex of degree 3, but G1 is not having. That is one. And another way you can say is G2 has a pendant vertex, but G1 is not having a pendant vertex. Where is the pendant vertex here? Here. Its degree is 1 now. It has pendant vertex, but other G1 has no pendant vertex. Okay. So now let me give you one more graph. So this is G1. Now let me take G2. So if they are not isomorphic, then what is the reason? No. Okay. Now let me do one thing. Let me give names to the vertex. Let me name this as A, B, C, D, E. So here let me name it like X, Y, Z, U, B. Okay. So now, yeah, tell me. It has 5 vertex. That also has 5 vertex. Number of edges are same. Yeah. G2 has pendant vertex. Easy. G2 has pendant vertex, whereas G1 is not having a pendant vertex. Is that the only one which is differing? Is there any other guy which is differing? Only pendant vertex or anything else? Degree of V, yeah, degree of V is 4. But in graph G1, there is no vertex of degree 4. Correct. There are two things we can say. Now let us look at few more interesting graphs. So here the vertices are here. I hope we can see them. These are the vertices. The corners are nothing but vertices. Total there are 8 vertices. So as of now they are isomorphic only because both are same graphs. They are not different. Now here let me take an edge here and an edge here. And when it comes to here, let me take an edge here and an edge here. Right. Now R is isomorphic. Now there are 8 vertices, right? Now let's do one thing. Let's see whether are they differing by degrees or not. Okay. So let me look at the highest degree in G1. First, let me write the degree sequence. What is the highest degree here? I hope 3. Yeah. So 3. Let me name that as A. And the next one is here. B. Its degree is 3. And next 2 degree terms. Oh, there is one more. C, D. Right? So these are of degree 3 and 3 only. And when it comes to the other, let me take E, its degree 2. F, its degree also 2. G, its degree is 2. H, its degree is 2. Now let me come to this graph. So here, okay, let me give some other name. Numbers are not good. Let me use capital A, capital B. Okay, so capital A, B, C, D. All are having degree 3 only. 3, 3, 3, 3. Okay. So when it comes to the other, E, F, G, H. So they are all having each of degree 2. So both graphics are same here. Both sequences are same. Alright. So number of vertices are same, number of edges are same, and number of, the degrees of vertices are equal, degree sequences are equal. Now can we say that they are isomorphic? Okay, if you say, if your answer is isomorphic, write an isomorphism. Like how do you map? So if you have an isomorphism, definitely adjacent vertices will be mapped to an adjacent vertices only, right? And one more thing is the connection is also important. Here you look at E, right? So if you look at E, this is of degree 2, right? And if you look at the adjacent vertices, what is degree of B? Degree of B is 3 and degree of A is also 3. Okay, but now let me see it here. Let me look at a vertex of degree 2 in G2. So the vertex of degree, sorry, what is the degree of E? That is 2, right? And you see its adjacent vertices. So it has a vertex of degree 2. Okay, but you see here both edges are of degree 3. You look at the neighbors of E. So the neighbors of E here, their degrees are 3. But when it comes to this graph, here you have only one neighbor of degree 3. Another neighbor is of degree 2. In other words, we can say it in another way. You take all these vertices of degree 2. Okay. Now it has a neighbor with degree 2. For example, G has a neighbor that is H whose degree is 2. Even H has a neighbor that is G whose degree is 2. Similarly, E and F. Okay, but it is not happening in this graph G1. Okay, so what is it you're saying? What if we map E to G? Okay, so you'd like to map E to where is this E to G here?
Small e to capital G, sir.
Okay, fine. Then I'll talk about this G. And where do you map this G?
H, sir.
Okay, so let us try to do one thing. Let us try to think about an isomorphism here. So you are mapping small e to capital G, all right, and small g to H. Okay, what else? Small e is mapped to capital G here, fine. And how about small h? Where do you map? So the small h is mapped to F. Then there is one more vertex of degree 2 here. What is it? That is F. Okay, where do you map F now? F is mapped to which is left. I hope capital G H F is over. So capital E is left. All right. Okay. And what are the other mappings you are taking? So we are left with A, B, C, D. So what are the other mappings? A, B, C, D. A will be mapped to where do you map? Again, there is a problem. You see, the A is of degree 3, and you look at the neighbors. Okay, it has one neighbor of degree fine 3. Here, A is of degree 3. It's not one neighbor. There are two neighbors. The degree of B and the degree of capital C is also 3 here. Now, where do you map A? So total how many edges we have here? 1, 2, 3, 4, total 8 you'll get, right? 5, 6, 7, 8. So now where shall we map capital A, B and C and D? Let's assume that I am mapping it to capital A, okay, capital B, C and D only. So now let me look at the 8 edges which are here in the first graph. What are the 8 edges? First edge is A, E. And the second edge, what is the second edge here? AH. And the third edge is HB. And the fourth edge is BE. And 5, 6, 7, 8. Alright, let me write it. So 5 is DF. How about 6? GD. And 7 FC. 8 GC. Okay. Now let me see the images. Now if you look at the images now, what is f of A? I'm directly writing the images, okay? What is f of A here? That is capital A comma small e is mapped to G. Do we have an edge A comma G? I hope no. A, between A and G there is no edge. This edge is not present. Okay. Therefore, this cannot be an isomorphism because this edge is not present. Okay. Similarly, you'll try for the some other assignment. So total number of 1 function from an 8 element set to 8 element set or 8 factorial, right? But no need of checking 8 factorial here because we have a restriction, no? This ABCD can be mapped to capital ABCD and this small EFGH will be mapped to capital EFGH. So 4 factorial into 4 factorial you'll get. So you'll get 24 into 24, that means not 8 factorial. Okay, so that many functions we need to verify, right? You need to anyway we have written these edges now. So similarly, you define the function, you write the corresponding edges, and you check. So definitely, at least you will find at least one edge here for which the images are not adjacent. Okay, initial itself we got failed, and if I take A and H, AH is mapped to AF, but do we have AF here? AF is also not there. Okay, so here the degrees are same, vertices are same, edges are same, but the thing is the neighbors are not same as here and there. I mean, so here what we can say is E, every vertex of degree 2 has an adjacent vertex of degree 2 in G2. Okay, but it is not true in G1. Example, we can say that E is of degree 2, but you see the neighbors of E. A is of degree 3 and B is also degree 3. E is of degree 2 and adjacent vertices of E are A and B. And how about degree of A and degree of B? Degree of A equal to degree of B equal to, that is 3. Okay, so we can say that these two are not isomorphic. G1 and G2 are not isomorphic. Okay, and if we discuss what is a subgraph and a graph induced by a vertex set, we can discuss in that sense also. In terms of subgraphs also, we can say two graphs are not isomorphic. Okay, that I will tell you. I'll discuss after discussing subgraph. Okay, and there is one interesting theorem which is about marriage hall, right? It is about matching. But we will discuss that in later classes. Alright, so this is all for today.